Okay, IP tables, the end of an era. So Antonio and I had had this talk idea, and then we started doing stuff, and it turns out that we had sort of different ideas of what the important things to talk about were. So I've got a bunch of slides, and he's got some slides. We'll be talking about, so a little bit about how networking in Linux works, just in case you don't know, to provide some context. What's wrong with IP tables, why we are moving to NF tables, and some lessons learned. But the TLDR of all of this is, don't use IP tables in new projects. It's old technology. It's going away. You should use other things, and we will talk about what some of those other things are. So this is the Linux network stack, sort of. There are a lot of versions of this diagram. All of them are actually wrong. And for our purposes, we'll just work with this model. A packet goes in, it goes through a series of tubes, and it comes out. So NetFilter, which is the system below both IP tables and NF tables, the idea is that there are certain points within the series of tubes where you can do certain well-defined things on your packets. And so kubeproxy, the most commonly used kubeproxy mode uses that. Calico is based almost entirely on IP tables. Other things use some IP table stuff. It's a simple model. It lets you do useful things. That's why a lot of stuff uses it. Another possibility within the kernel is OpenFlow. Antria is based on that. OVN Kubernetes uses OVN, which uses Open vSwitch, which uses OpenFlow. It's a little bit weird in that Open vSwitch is a software implementation of somebody else's standard. It's OpenFlow. So your packet goes into the kernel, and then it goes into OpenFlow, and which is this completely separate series of tubes that it can go through, and then it comes back out and then leaves. And so it's barely part of the kernel network stack at all. But you can do a ton of cool stuff when it's in the Open vSwitch part. Then there's eBPF. So unlike the IP tables model, where you have like this well-defined set of things that you can do, eBPF's model is you can plug in so many different places. There's definitely a cluster of places you can plug in right at the beginning where the packet goes in, and a cluster of places where you can plug in right where the packet comes out. But in general, anything goes. You can do all sorts of weird things. It's cool. So here's everything together. The weird thing is that none of these pieces really work together very much. IP tables, like Open vSwitch mostly bypasses IP tables rules. It completely ignores eBPF. IP tables and eBPF don't interact all that much, although they're working on that apparently. So you kind of have to pick one technology and go with it. So we had picked IP tables for kubeproxy, and now we're moving away from it. So why? Well, so mostly there are problems with IP tables. The kernel developers are moving away from it. They started work on this new thing, NF tables, which is the replacement for it. It has all these new features. It has better performance. And they're just not working on adding features and performance to IP tables anymore. Red Hat has announced that it's completely removing the IP tables APIs from the kernel in RHEL 10, which means a few years from now, the IP tables kubeproxy won't even work anymore on RHEL-based Kubernetes clusters. So we needed to do something. And this leads to the question of, but if they're both based on NetFilter, how come NF tables is better? So, okay, what are the problems with IP tables? In an IP tables, I hope people can see the text. In an IP tables-based system, you tend to have a rule for every possible thing that you want to do. So we have some kubeproxy examples here where you have this kube services table and you say, okay, well, if it matches this destination IP address, then jump to this chain. And if it matches this destination IP address, then jump to this chain, and so on and so forth. And every packet needs to get checked against all those rules. And so, this works fine if you have a firewall with 50 rules or whatever. But if you have 20,000 Kubernetes services, that's a lot of rules and a lot of rules that the kernel has to check on every single packet that goes through, and that makes things slow. In NFTables, it has all these cool data structures like sets and maps. And so rather than having a separate rule for every service, you just have one rule. Wait, I've got a pointer. Where'd my, I had a pointer. Oh, there we go. So you have one rule which says, look up the destination address in this map and do whatever it says. And then you create a map that has all of these mappings from IP address to chain, and then each packet only has to get matched against one rule, which does a hash table lookup to do the right thing, and it's much, much faster and more efficient. So the other thing, so that's on the packet processing side. On the rule processing side, Iptable is also terrible. It was designed with these small firewalls in mind, not with 20,000 services. So if you have 20,000 services and somebody adds one more, and you want to go to 20,001 services, you have to get a lock, download the entire rule set from the kernel, add one new rule at the bottom, upload the entire rule set back to the kernel, and then release the lock. This has been a source of problems. It makes the Iptables kubeproxy slow. It takes it a long time to process changes. We do all sorts of clever things in kubeproxy to get around this, but fundamentally the API is just hard to work with. Again, NFTables fixes this. You just say, I want to add this one rule. It adds that one rule. Done. Another problem that Iptables has is that, again, the idea, it's a firewall. So you only have one firewall in your system. It manages all the rules. It owns everything. It can do whatever it wants. So usually, if you're running a firewall on a Kubernetes node and you restart the firewall, it will delete all of Kubernetes rules because it thinks that it owned all the rules. And so Kubernetes has to deal with this by occasionally polling Iptables to see if somebody deleted all of its rules behind its back. NFTables solves this problem. Everybody gets their own table. Firewall puts its rules in one table. Kubernetes puts its rules in a different table. Nobody messes with anyone else's table. Everyone's happy. So you may remember something about Iptables legacy versus Iptables NFT, where Iptables NFT is a reimplementation of the Iptables command line API that instead of speaking the Iptables API to the kernel, it creates NFTables rules instead. And basically all of the distros are using that now. So the legacy Iptables API actually really doesn't even exist anymore. It's still in the kernel, but nobody uses it. The problem is this doesn't actually help all that much because it's still conforming to the old Iptables command line APIs. You can only use the features that were in Iptables, and you're stuck with the restrictions that API imposes, which means you can't even get any of the efficiency things because since we're working around the problems in Iptables API where we have to download all the rules and upload everything, we still use it the same way in Iptables NFT, which means that we can't actually get it to update one single rule at a time when we want it to. So Iptables NFT doesn't help. And some people are like, well, why did they have to invent NFTables? Why couldn't they just make Iptables better? Well, if they had made Iptables better, we would still have to rewrite kubeproxy because we would have to use completely different APIs anyway. So starting new let them, it was just easier to fix things that way. What about IPVS? So we have this IPVS-based kubeproxy backend in addition to the Iptables one. It's definitely faster in some ways. Antonio will hit me if I say that it's faster because we haven't actually done testing to show that it's faster, right?
It is faster.
Okay. we don't have a lot of E2E testing, but yeah, we're pretty sure it's faster. So the problem is that IPVS is just this one tiny little thing in the kernel that only does one thing. It does like load balancing and rewriting packets from service to endpoint. But Kubernetes services need a lot more than that. So you end up needing to write a lot of glue. to add all of the other Kubernetes functionality on top of IPVS. And right now, all of that glue is in Iptables. So even if we wanted to keep using IPVS, we would have to rewrite all the Iptables rules, use NFtables. And at that point, you lose a lot of the benefits that the IPVS backend had over the Iptables backend. It didn't really seem to make sense to try and extend that more. It seemed like just going to NFtables would result in a simpler and better kube proxy than trying to extend the IPVS one a little more. What about OVS? There are people using OVS for service dispatch, notably Antria and Ovian Kubernetes. So when I showed before that OVS is kind of this completely separate path within the kernel that doesn't interact with everything else, that means that it's great for if you want to write your entire network plugin in OVS in OpenFlow, but it's bad for something like kube proxy where we're just solving one part of your network problem, rewriting services, but you still need pod-to-pod transport and network policy and stuff like that. It's hard to mix something based in OVS with things that aren't based in OVS. So if we had done kube proxy this way, it would have been really hard for anyone else to incorporate it into their existing network plugins. So that was no good either. What about eBPF? Obviously, Cilium uses eBPF. Could we have done that? Yes, we could have. Would we have wanted to? Not clear. So I like to say eBPF is like a Swiss Army knife. Like, it's small, you always have it, it can do like all these different things, but it's not always the best tool for the job. Like, if you've got a better tool, it will probably work better than eBPF. And in this case, for implementing kube proxy, we need a tool that lets you NAT packets and lets you drop packets. And that's what Iptables and NFtables do. So we could have done kube proxy and eBPF, but eBPF is a little hard to work with. You have to write code in C or Rust or something like that, and then compile it to bytecode. And we don't have as much expertise in those languages within the Kubernetes community and within SIG network. The eBPF itself, you need to understand like the kernel data structures for working with network packets. It gets really confusing. And then you have to get past the kernel verifier. With great power comes great responsibility. Since eBPF gets run by the kernel and can do all this stuff, the kernel has to be like really, really careful about what it allows to get in. And so it makes sure, for instance, that your eBPF program will terminate, which means you aren't allowed to have unbounded loops, which makes it really hard to do a lot of things. Network policy I put because that's something that I had actually tried implementing before. The obvious way of implementing network policy is like, you have your policies and you just say, okay, here's a rule for this policy and here's a rule for this policy and here's a rule for this policy. You can't implement that in eBPF because you can't just say, for I equals 1 to number of policies, check this policy. So instead you have to figure out some way to take your complete set of network policies and convert them into maps where you can do lookups of all the things. And you can do this. I mean, Cilium does it. But it requires you to totally turn your problem inside out, which again makes the code harder to understand and less intuitive to people who are familiar with the way that it works in Kubernetes. So again, like with OVS, there are certainly places where using eBPF is a great answer, but it seemed like kube proxy is not one of them. I think this is yours now.
So this is the KEP that Dan is leading, that is to move kube proxy to NFTable. So if you want to read more about this work, you just go to the KEP. The KEP is awesome. It's impressive. You need to read it. I printed it. So and I want to talk more about what the non-network guy, the Kubernetes user is going to see with this problem, right? So right now you have a Kubernetes cluster you are using basically for the 90%, I don't know, I'm making up the numbers, but the majority of the cluster are using Iptables for the following thing. For services with kube proxy, for the CNI plugin, for doing port map or another stuff, and for network policy, right? Those are the stakeholders of Iptables in a Kubernetes cluster. And those are the components that are going to be impacted by this change. The way that Dan was explaining before is back in the time, we have an Iptables kernel library, kernel API, that with a user space library, right? So the kernel developers created the NFTables API and the user space library. But as you can see, we cannot move from one place to the other, right? Not breaking all the clusters. So what they created is a new user space library that is the Iptables NFT, right? So then with the same link, users can choose one or the other one. And theoretically, you can migrate with zero disruption. But the problem is that there is no zero disruption in this, because when you are using Kubernetes, you have two different Iptables binaries. And this was a very painful problem in Kubernetes that it took a while to resolve. So maybe your pod has the legacy version of Iptables that is going to program the all kernel API of Iptables, and the host has the NFTables backend. So both can have a mismatch, and then things are not going to work in your cluster. Things that we saw before that can be services, network policies, or pod creation. So basically, all the important things in working in the cluster are going to be screwed. And as you can see, we hit these two. These are the more representative issues caused by this problem, by this mismatch. And the way to solve this problem is just, Dan Winship created this useful tool that is a script that detects what the host is using and what binaries you should use in your pod depending on this or the other. The other lesson learned that we know that is going to happen for NFTables is that right now, a lot of components depends on this Iptables binary. So if you have any component, any project that is depending on this Iptables binary, you start thinking in switching to the new NFT binary. And this is going to be the new problem that we are going to have to face with this migration. And I think that's it. I don't have anything else. Everything has a cost. We are moving to a better place, but the people with projects and the user need to face all these migration issues that means moving from one library to the other one. Okay. So, any question? Any question about Ricardo? Yeah, go. No, Ricardo was first.
Going back to the question of whether IPVS mode is faster than Iptables mode,
okay.
At my day job, we're no longer using kubeproxy, but at some point in the past were and had to use IPVS mode for performance reasons, like IPVS mode's very good. This makes me wonder, is NFTables mode comparable to IPVS mode in its efficiency when you have services that have large numbers of backend endpoints, when you have large numbers of services, things like that? Like, is there a chance IPVS mode might disappear if NFTables mode is so much better than Iptables mode that it's not needed anymore?
Okay, so starting from the end there, we haven't figured out exactly what is going to happen in terms of, we have landed the alpha version of the NFTables-based kubeproxy in 129. We haven't figured out what's going to happen with that versus Iptables versus IPVS, other than that we don't want to be maintaining 3 backends forever. So hopefully it will be faster than both of them and implement all the same features and solve everybody's problems, and then we can just get rid of Iptables and IPVS. The other possibility is that we might possibly push them out of tree, like what happened when we deprecated Docker shim, and pushed cry, Docker, whatever out of tree so that people who want it can still use it, but it's, then they can figure out who will maintain it. The current alpha version of the Iptables kubeproxy we have not tested yet, so we can't tell you if it's any faster. There have been other Iptables based kubeproxy attempts in the past, and they got very good results. In particular, like I was saying, a lot of Iptables problem is that you've got this list of 20,000 rules that it has to go through, and Iptables, like IPVS, does not have that problem. It is still going through, processing rules rather than just being hard-coded load balancing functionality like IPVS. So it's possible that IPVS will have some advantage over it still.
I want to touch a bit on this faster thing, because there are always a lot of, this is a problem with several dimensions, right? So Iptables is slow in the first hit. Then you go through the contract and then, so the problem is slow in the first packet. Later you go through contract, right? Then the main problem in Iptables is not that one. The main problem is the programming latency. So you need to send to the kernel, I don't know, with 100, we have this number, right? I don't know how many services, it takes like 6 or 10 seconds to program. So you have a 10-second latency to program your services. The other thing that I care a lot about is about the stability and predictability, right? So you may have a super fast thing, and you can have a high variance and percentage on programming latency that, keep going up. And the good thing of Iptables is that it's stable. It gives you 5 seconds, it's 5 seconds clock. So that's the other thing in networking that I don't want people to go to, oh, this is faster. Well, maybe it's faster for the team, but when you have 100 services all hitting the data plane, you want to be stable too, right? So that's the point that we now in beta, we are going to hammer in Iptables to get these numbers and see if it's faster, reliable, and all this stuff that we want.
Thank you.
Yeah.
Thank you. And?
I'll make the question when they're going to be really
No.
upset with me. Can I create Ingress Iptables? No, I'm just kidding. I've not been in the meetings recently, so I don't know what's the status of Kaping and how. I know that Kaping has been actually the attempt to make the Iptable stuff and been pluggable, and we have the short-term problem to be solved with Iptables. So I just wanted to understand what's the C goal on that, like if we're going to kill that or if we're going to keep trying to make some control plane, data plane, kubeproxy approach. And that's an honest question, that's not a joke.
So first, the Kaping Iptables backend was very much just a sort of proof of concept thing. It didn't try to use any of the good Iptables features, so it wasn't really a good starting point for updating kubeproxy. As for Kaping in general, so basically, people went off and did all of this stuff and came up with this new architecture and all these new ideas of how to implement a proxy. And it was just a huge amount of code, and nobody ever finished the KEP for it. And so it wasn't clear if SIG Network actually wanted it. And at this point, I think, the Kaping project or the people behind that are still just working on backends there. It's possible that the Windows backend might get moved to a Kaping-based base. Yeah, for the replacement Iptables kubeproxy, it seemed to make more sense to just build it based on the existing kubeproxy code base.
For me, the key thing is that it wasn't passing all the tests. And we need to, this is a core component. We need to have a super high bar on performance and quality, right? If it's not passing all the tests that we have, that we know are not enough, we cannot keep iterating in tree to improve something.
Any other questions?
So as part of some of this work, are you going to be able to consolidate some of the code for the backends? Like I know a lot of the code was like duplicated for various backends. Like, are you gonna be able to move a lot of the shared stuff into one place, so then maybe it'll be easier to deprecate and even add? Granted, I know we have no appetite for adding new backends, but.
Yeah, there's been some refactoring of the kube proxy code going on in parallel with this and still continuing. And hopefully we will get it to a point where we can pull the useful parts of it out of KK and put them into, like, stage them into case.io/kube proxy, so that out of tree service proxy implementations would be able to reuse that core service and endpoint slice watching and you know, compiling whatever code.
Sweet. Yeah, that was the point. And you don't have to do all the caching that you used to have to do for the Iptables rules, right? Like there was like some crazy caching infrastructure there. So
I don't think that you're going to be able to get rid of the cache.
Yeah, I'm not. There was no crazy caching. There's just normal caching.
Any other questions? Yes.
This is really open-ended, but what would it take in the kind of eBPF kernel space for that to become more viable for this kind of thing? Like, run it down a little bit.
Well, I am working with Syrian community lately, and they have an implementation. The problem is that we in Sig Network did something wrong. That is, we leaked a lot of the implementation details on kubeproxy in the service API, right? So now the problem that we have, and Dan has a good document about that. The problem that we have is when somebody asks us, oh, how this new field works. And then what we do is, oh, let's see how kubeproxy does, right? And that's it wrong. And we have these problems with, for example, affinity, right? Affinity works one way in Iptables, other way in IPVS, another way in Syrian. And that's something that we have to improve as Sig Network defining API. For your question in eBPF, it's totally possible to do it. The problem is as Dan said, do we want to go down that path? Are we going to get something from that? Is feasible? Is sustainable?
Too open-ended right now, right?
Yeah, that's, I mean.
Well, I mean, it's not an API for anything in particular, right? It's a very general purpose API. And so, yeah, you can do it, but you have to work in C and understand the kernel data structures and all this stuff. Or Rust, yeah. You know, I mean, like I was saying, it is totally a viable option for, I don't know if you're asking in the context of whatever the Ingress thing using eBPF. But, So I can repeat that. Yeah, sorry. So he was asking, you know, what our evaluation was, and I mean, it is a good technology for some projects. It didn't seem like a good technology for something that Sig Network would have to maintain, where there was already another technology in the kernel that does exactly what we want.
Yeah, and that actually seems totally fair to me. I can see it. But yeah, thank you. It was open-ended. Thank you.
One important thing is the Kubernetes is the service API. We have kubeproxy that is an implementation, right? It's an implementation detail of that API. So we are not betting on one technology or the other. We just pick the one that was solving the existing problem. That's why this talk was about. You saw all the problems, all the feature problems, and we needed a solution. And this crossed most of the checks.